Awesome. Chris, that's for my graduation party.
In the building they built?
It probably cost them like a couple.
If you get this in count.
That's what I'm guessing. But they're loaded. And then they have so many people at the school. They have so many people in their family that just.
All right, let's go ahead and get started. So, in lecture, last class period, we were talking about called equilibrium. And there were two conditions for something to be in what we call static equilibrium. And that is that the forces on an object are zero, and that the torques on an object are zero. So, two conditions for equilibrium. Now this is mechanical equilibrium, so for an object it's quite different from like thermodynamic equilibrium, that you deal with maybe in chemistry. Okay? Static equilibrium. One, the sum of the forces on the object is zero. And two, the sum of the torques on an object are zero. So this means that the object's not accelerating. This will end up meaning that the object isn't accelerating in its rotation, what we call it isn't picking up a rotation. So yesterday we introduced what the definition of a torque is. Torque, symbolized by a tau. What was it?
R perpendicular times.
R perpendicular times the force. So there's a torque associated with every force. If I have a pivot point, say here, that'd be the pivot point. And if I exert a force on an object that can pivot, the torque associated with it would be the perpendicular distance from the pivot point to the force times the magnitude of the force. Okay, and it's positive if it causes a counterclockwise rotation. That's the convention we'll use in this class. And it's negative if it causes a clockwise rotation. So this would be negative or positive torque due to this force.
No.
Negative.
Negative because it's making a clockwise rotation, right? And that's a convention we'll use. You have to keep looking at the problem from the same standpoint doing that because, if I look at it this way, this is a clockwise rotation. If I imagine I'm behind the object, it would be a counterclockwise rotation. So you have to maintain kind of the side that you're looking at the object from, okay? Does that make sense to you guys? And we did several examples where it was easy to see what the perpendicular distance between an object was. So today I'd like to do a few more examples of that. And we'll see something where it becomes a little bit trickier to apply this definition of torque, and we'll create another definition. So for this one, if you look at your arms, your arms are kind of interesting. Your elbow can be modeled as a joint, like a hinge. So this is a model of an arm. And if you look at what's happening when you bend your arm, what's going on is you have a muscle that is your bicep that's exerting a force upwards. So if I have it's out a little distance from the elbow. Okay. And it'll actually attach, your biceps attaches to your upper arm. So if I were to draw this model of an arm, it's going to I can imagine that I have some sort of cord, like your bicep, that can exert a force that would pull your arm upwards. So a good example of where the torque is, where we're dealing with torque is, just looking at like how much force the actual muscles have to exert to move your arms around. It's you'll find it's quite a bit more than actually what you're lifting. And so let's go ahead and maybe see that. Let's say I have a 10 kilogram mass here at the end of my arm. That the arm itself weighs about 2.5 kilograms. The forearm. Let me see if I can get these measurements correct. That the length of the forearm is 40 centimeters from here to here. That the length from the elbow to the center of mass of the arm is 15 centimeters. Center of mass, we'll talk more about that next time, but this is effectively where gravity acts on the arm. And the distance between where the bicep attaches is 4 centimeters in the elbow. Okay. Let's go ahead and see if we can use our knowledge of equilibrium, that is the torque, in this case the torque's being 0. Let's see if we can figure out what the force is going to have to be applied here. Okay. So I want to figure out what the tension force is in the bicep, the magnitude of that tension force, so that the arm can be, bent. Make sense what the problem is? All right. Oh, this meant was bicep. Well, let's go ahead and see if we can look at the torques of all these different forces. So at the end of this arm, there's a 10 kilogram mass, about 22 pounds. Let's just kind of label the forearm. I'm going to draw it here. I have a tension force going up like that. I have a weight force on the arm. I'm going to call that the first weight force. And then I have a weight force due to the mass that it's holding. Let's call this mass M1, and then this mass M2. Yeah, M2 mass M1. Okay. So and then this distance here is, let's call it R2, and then this distance here we'll call R1. All right, so it's pretty easy to, in terms of these R's, to figure out what the torque is due to this weight force. What would be the torque there?
Weight 2 times.
All right. Torque 2 would be R2.
R2 times weight.
Weight times the magnitude, weight 2. Does that make it want to go clockwise or counterclockwise? About this pivot point.
Clockwise.
Clockwise. Clockwise, right?
Clockwise, yeah.
So it'd be negative. And what would be, and what's the magnitude of weight 2?
MG.
98.
90.
That's right. This I'm just going to write this as M2V. Okay? Good. My torque due to the first force, what would that be?
N1G times
M1G, okay.
R1.
Times R1,
Positive.
and it's positive?
Negative.
No, it's
It's
negative.
negative.
Negative, okay, good. Now, let's go ahead and look at this tension force now. Okay? This is where it's gonna get a little tricky. See, if I look at this tension force, if this tension force were exactly perpendicular, this would be easy to get the perpendicular distance, it'd be that 4 centimeters, right? In actuality, it's not quite. Oh, I forgot to mention one other thing. Your bicep attaches, your forearm goes up to and attaches near your shoulder. And if you measure that, what's the stroke head, it was something about like 20 centimeters. Okay? There.
So we have an angle theta?
Yeah, you have an angle here. So it doesn't quite, so so we want the part of the radius that's perpendicular to this force. So let me see if I can draw this a little bit. Let me kind of expand my drawing. So I'm taking this little bit of the triangle, right? And I'm kind of expanding it so I can see that it's a bit more of a triangle. And it's not going to be, it's not drawn in scale, right? So this is 4 centimeters. This way, this is 20 centimeters. This way. And I have a tension force going upwards like this. Now this is the distance between the pivot point and where the force is applied, but that's not the perpendicular distance. This would be the perpendicular distance, wouldn't it? So how do I get that? That's kind of tricky, isn't it? Well,
Well, you know,
Theta.
so it's not a right angle when you
It's
cut
gonna
it.
be cosine.
Oh, you
If
can
one
solve
of
for
them's
the angle
90,
in
then
the
the other
first
two are
one.
45.
what's that?
If the one on the top is 90, then the other two have to be 45.
No, this one's, they don't have to be 45, but they have to add up to 90, right?
Mm-hmm.
You can
Oh, yeah,
solve.
okay.
Yeah. Well, I know this length, right, 4 centimeters?
Mm-hmm.
And I know this length here, 20 centimeters.
So you can get the hypotenuse.
So I could get this, can I get that angle?
Oh, yeah.
And I'll call that theta. What would theta be? Let's look
Theta.
at this big triangle.
Arc,
So that's
20 over 4 centimeters. Arctan
So tangent
over adjacent.
of theta would be equal to
Opposite over
opposite.
adjacent.
This is for this big triangle here.
Yeah.
This 20 centimeters, that's the opposite side, right? And then what would be the adjacent side? This one. Be 20 centimeters over 4 centimeters, which is just 5. So I can say theta is inverse tangent or arc tangent of 5. What is that, by the way?
78.7.
78.7 degrees. Okay, so now that I know this, let's look at this little triangle here. I know this side length, 4 centimeters.
Mm-hmm.
I would like to be able to get this side length here.
So you can use 4 centimeters cosine of that angle.
Well, yeah, is this the opposite or adjacent side to that angle?
Opposite. So it'd be sine of.
Yeah, that's the opposite side, right? So our perpendicular over 4 centimeters, that's this side over the hypotenuse, is going to be what? So
Opposite.
it'd be the sine of that angle, right?
Mhm.
And so our perpendicular would be 4 centimeters sine of that angle. What is that equal to?
3.9.
And that'd be 3.9 centimeters. In our case, it's not a huge correction. Okay, let's look at the torque due to this tension force then. I'll just write that torque due to tension. It would be the magnitude of the tension force times the perpendicular distance, which we just solved for, right?
Mhm.
So 0.039 meters. Is that good? All right, now, let's, we know all these. Let's see, can you guys evaluate what torque 2 is and evaluate what torque 1 is? I'll need a couple, at least a couple numbers and maybe checks. I'll write 2 of these just in case, so we get a good, make sure we evaluate it properly. So what was R2? Yeah,
Mhm.
so if I wanted to write this in SI units, 0.4, yeah. Meters. So what did I get?
$39.2, yeah.
Negative 39.2 Newton meters. What was this one? Did anyone get anything different than this? Okay.
3.67 or 68.
3.67,
68.
68 Newton meters. The minus sign, right? Anyone get anything different than this? All right, now if this thing's supposed to be in equilibrium, what are the forces on it? By the way, there's also force on the elbow. Would that exert any torque? Because R perpendicular, the R is 0 because it's at the pivot. So there's no torque with that. So if I wanted to sum up the torques, what should the result be?
0.
So yeah, so torque 2 plus torque 1 plus the torque due to the tension is 0. That's the condition for equilibrium, that I'm able to hold that. Yes,
Wouldn't there be force on the elbow?
there
since
is,
it's being held?
there is, but what's the perpendicular distance of that force from the pivot point, which is the elbow?
3.9?
The pivot point is the elbow, right?
Oh, yeah.
So there is a force on the elbow. Let's say it goes this way. The torque due to that force is 0, because the distance from the pivot point is 0.
Oh, because it's not moving?
It's moving, but the distance where of the force on the elbow, from the elbow, is 0. Because
Okay.
because the force applied on the elbow. Does that make sense? So the torque is the force times the perpendicular distance of the force from the pivot point. So this is 4 centimeters, right? And we found the perpendicular distance to be here.
3.9, yeah.
This was 15 centimeters. The force here was 40 centimeters. What's the force here is right at the pivot point.
So it would be 0.
Yeah.
Fair enough.
Okay. All right, let's plug in numbers here and what we know. So all I'm going to do is I'm just going to take what I know, put them in here. So I get minus 39.2 Newton meters minus 3.68 Newton meters plus magnitude of tension force times 0.039 meters is is equal to 0. Can you solve for this tension force now? Go ahead and do that. Get it, Larissa? What'd you get?
1099.5.
Yeah, that's what,
1,099.
0.15.
Yeah.
I just have a quick question.
Yeah.
I'm not getting negative 39.2.
Okay.
Are you supposed to do the whole 40?
No, 0.4 meters. It's 40 centimeters, okay?
Do we not take off the 4 centimeters?
No, because the pivot point is the elbow.
Okay. I was.
Did everyone get this? All right, so basically your tendons have to be pulling the same, to lift this 10 kilogram mass, it has to be pulling the same as lifting up like a 110 kilogram or 220 pound object. So those, they're doing pretty good. There's a lot of force on tendons, and that's how you can injure yourself quite well. By the way, it's interesting to look at different skeletal structures. Humans will never be as strong as, say, chimpanzees, right? Even though chimpanzees don't look very big, but their attachment points of their muscles are much further out on their arms. And so they just naturally will be able to lift more just from that, but they won't be able to move as fast. So it's kind of so if you want to move your arm fast, up and down, you'd want an attachment point close, because then, if this pulls just a little bit, this arm would go up quite far. If you want it strong, you'd put the attachment point out further, and then you would have a lot more torque lifting up things, and you'd be able to lift up a lot more. So, it's just one of those things, like, it depends on what you're meant to be doing, how strong you'll be. But there's limits, of course, on this, like, the attachment point of the tendon into the bone can only take so much. And, maybe you've known people that have detached a tendon or something by trying to lift something too much or have a jerky motion or something. So did it make sense to you guys? You want to do another example? This one I'll introduce. I think I want to introduce something that will be helpful. Okay. Yeah. I'll do this with an example. So let's say I have a wall here. Okay, for these problems where I have like the bicep pulling here, it becomes a little, we sort of derived this R perpendicular in an effective way, and but going through that was a little cumbersome, right? There's a lot of geometry there. So I'm going to introduce a slightly different way to do this that you can also use as the definition of torque. And it's helpful when you have like a wire at an angle. So let's imagine I have a boom. Let me see if I can draw this. And I want to figure out, and it's attached to a wall, so that this is some angle, theta here. And then this is a wire that's holding up this boom, which is just like something solid, like either a piece of wood or metal or something. All right. Then it's really easy to figure out the distance from the pivot point to where the force is applied, like that. That's just the length along the boom. But figuring out the perpendicular distance is a little tricky. The perpendicular distance would be this, wouldn't it?
What is that, R1?
And then
R
so
perpendicular.
R perpendicular, yeah. So I'm going to draw the tension actually along here. Okay, no, this is not a very good color. You can't see it here. Okay. So I'm going to draw the force as a little red line, right? And then this would be our perpendicular, like so. So our perpendicular times the force, let's call this the force here, right? The red line is the force, is a force vector. I can sort of look at this as geometrically, right? Although this isn't really a length, it's just a vector with a magnitude with the units of force, I'm going to treat it as sort of a length, okay? And in this case, R perpendicular times F, I can think of as related to the area of this triangle where I have force on one force length here and then an actual force length here. So the height of this triangle is R perpendicular. The width of this triangle is F. So this area is equal to R perpendicular F divided by 2. Because the area of a triangle is base times height divided by 2. So, actually, that is the same area as if I had drawn a second triangle and looked at this whole square, isn't it? So this can be thought of as area of square. Now it's not a real area because one side's a force and one side's a length. Or maybe not a square, area of rectangle. Okay. Now this is confusing, I know. If I look at this side length, this is the component of the force that is perpendicular to this radius here, right? I'm going to call this F perpendicular. And then this R. So I can also write that area of the square as equal to R F perpendicular. So this is another way to write the torque due to a force. So the torque will also be written can also be written as either perpendicular distance from the pivot point to the force times the magnitude of the force, or the distance from the force to the pivot point times the part of the force that is perpendicular, the component of the force that's perpendicular to that, to this distance. Either one of those are equivalent definitions of torque. Sometimes it's easier to figure out the torque due to a force this way, sometimes it's easier to figure it out that way. When you have a guy wire at an angle, it'll be easier this way. So let's go ahead and do an example. I hope that was some derivation. I know it's a little confusing, right? It's
Because those all
geometry.
equal torque, right? Because R perpendicular times the force equals torque, so that's also the same as the area of the angle.
Yep.
of the rectangle. Okay.
Yep. So R perpendicular times the force is twice the area of this triangle, which is the same as the area of this rectangle where I put the two triangles together.
So, just so I didn't miss anything, the area isn't really useful for anything besides getting other values out of it, right?
Yeah, this area was just used to prove this.
Okay, good.
Yeah, we not have to deal with it ever again. All we needed was this. But I thought that the proof can be slightly enlightening.
Are we gonna have
It's a
to do
typical
problems
physics
like
type
this?
proof.
Are
What's
we gonna
that?
have to do problems like this a lot?
No. Well, you may have to apply this,
Okay.
but we don't have to do this proof.
Okay.
This proof
But we
is
still have to
tougher.
know that to realize we're gonna use that for torque, right?
Well, if you're happy to just use these two equivalent definitions, just use them.
Okay.
I like to know where they come from, that they're equivalent, and that's why I did that. So, but if you're willing to accept those definitions, you don't need to know anything besides them, okay? Yeah. That was probably a typical physics proof. If you like that type of thing, you might be a physicist at heart. So I'd like to do a problem with numbers. Okay. So this is going to be kind of a crane or a boom, okay? Okay, so what I have here is kind of a wire with a braking strength of 1,000 newtons. Okay. This length here is 0.5 meters. And then there's another wire coming down here, a little rope, and there's an M here. This length between here and here is 0.25 meters, and that's the same as this length.
So the overall length is 5 meters, but that little
It's 0.5 meters,
Oh,
half of a meter. 0.5 meters is the, is this overall length, okay.
and this is points of 5 meters again for the vertical.
What's that?
The,
It's 0.25
Okay.
between suspension point and where this wire is attached. Okay, now this hinge, okay, so what's the maximum? I want to figure out what is maximum M, I can hang from here. Hang from boom. And 2, what's the force on the hinge where it's against the wall? What's the force on the pivot point?
So we're simply looking at the shear strength of the wire. We're disregarding the attachment points as weaknesses, correct?
Yes, yeah, we're assuming that it might break here, okay, but we'll say that that's 1,000 newtons, okay. Maybe that's the breaking point of the attachment point. It won't matter. That's just the maximum the tension force that can be in here before something breaks. All right, I'm going to give you 5 minutes to try and work one out on your own. And I think that should be sufficient if you're good with these types of definitions. Yeah.
Pivot point where it moves the boom, that's where the boom can move up and down.
So pivot point's this point at the wall.
Is the other name on it?
Nope.
Well, they're
I know it's a quarter of a meter. That's just where the wire attaches. Oh, I didn't tell you the weight of the boom, did I?
No.
Just take it as massless, okay? Very lightweight. That's okay. Get this part. able to get this? Nobody?
That would be opposite.
I guess you could call that potential force area, there's a silver tension. You guys get it?
All right, well, we better go work on this then. Okay, I'll go do this one, and then, there's a couple examples in the book, you guys could do at least them, hopefully by next time.
Do you mean in the homework or in the chapter?
In the chapter, and then also the homework would be good.
How did you find this again?
Okay, so I'm gonna start out with,
45 degrees.
for these types of problems, it's just draw the forces on the boom more or less where they're at, okay? So it's like a free body diagram, so you just draw where the forces are at. So I have some sort of force of the hinge, I'm just gonna draw it this way. I don't know exactly which way it goes perhaps right now, but, you know, if I draw it this way and, you know, we can solve for it later. I have a tension force due to that hanging mass, and I might as well just call it that. I know that that force is going to be the weight of the mass. I'm just going to call that weight. And then I have a tension force that's going off at a 45-degree angle our way up. And that's it. That's the forces, right? Provided the boom is very lightweight. All right, this weight force would be the mass G downwards, right? This this tension force, that's what I want to figure out what that is. I'm going to set that equal to 1,000. Okay. Magnitude is equal to 1,000 newtons. That's at the maximum mass I can have here. All right, let's figure out the torque due to this. Torque due to this force is pretty straightforward because I just take that R perpendicular multiplied by this force. And is that a positive or negative torque?
Negative.
Makes it want to rotate clockwise, so we'll call that a negative torque. So torque due to the weight is negative mg times
0.5 meters.
0.5 meters. Okay. Is there any torque due to this thing? At the hinge? No, because that's a pivot point. So there's the R perpendicular is 0. No torque due to this force. Let's do the torque due to this tension. Well, I know I know this angle, first of all, will be the arc tangent of, you know, the same as this angle. And this is a quarter meter here. This is a quarter meter here. This is the arc tangent of 1, which turns out to be 45 degrees. So this would be 45 degrees here. Okay? Does that make sense to you guys? Okay, so this angle is 45 degrees. The tension force goes off like this, the R goes like this, that's the distance from here to here.
Mhm.
The perpendicular component of this force is this component. Right?
Why is it not from the pivot drawn that way?
You could just draw it that way too. Same component of force. So tension perpendicular is going to be the magnitude of the tension force times and this is the opposite side of this triangle, would be the sine of 45 degrees. And then this distance is a quarter meter, so I could do tension, sine of 45 degrees times this quarter meter here. And is that a positive torque? Yes. Yes, it is. All right, so these two have to be equal to each other, right? So I can do, well, I can do minus mg times 0.5 meters plus magnitude of tension force sine of 45 degrees times 0.25 meters. That's equal to 0. Sum of the torques is 0 in equilibrium.
So you're adding them together there?
Yep, I add them together, set the result equal to 0. That's my condition for equilibrium. And then I just have to, and I know I'm going to plug in 1,000 here, 1,000 newtons here. And I want to solve for m. So I could write mg, well, I can write 1,000 newtons, sine of 45 degrees, times 0.25 meters is equal to mg times 0.5 meters.
Divide that by.
Divide by g and 45 meters. Or 0.5 meters, sorry. And that'd be my m. And what would the result be? So it's about 700 and, this is 717, a quarter of that, which I have.
$36.1.
Yeah, that's about right. So m is 36.1 kilograms. Makes sense? That'd be the maximum that, mass that you can safely hang there without having that thing break. It'd be useful in practice, if you know what your breaking point of your boom is, you can now figure out.
For the torque due to the tension force, I did the perpendicular force times R. Is that wrong?
That's what I did. So our perpendicular was 1,000 newtons sine of 45 degrees. So.
Oh. It wouldn't just